So far in Chapter 1, we've examined two methods for solving differential equations. The first was by direct integration. If you have a derivative equal to a function of the independent variable alone, then you can solve by integrating both sides with respect to the independent variable. We call that solution method direct integration. The second case that we considered is when your first derivative is isolated and it's equal to a function of both the independent variable and the dependent variable. If we can write that right side as a product of a function of the independent variable and a function of the dependent variable, then we can solve using the process of separation of variables. We'd write all of the dependent variables on the left, all of the independent variables on the right, and then solve by integrating both sides with respect to the variable indicated by the differential term. But what happens if we have a differential equation of this form so that we cannot express the right side as a product of a function of x and a function of y? What if we have a sum of a function of x and a function of y over there? Well, in that case, we're going to need a different approach. So in section 1.5, we'll study linear first-order equations. We're going to look at a new method of solution called applying an integrating factor. So in this section, we'll learn the new method of solving with an integrating factor, and then we'll consider applications using this method. So let's get started on our integrating factor method. The first thing that we need to do is examine the definition of a linear differential equation. Now, I know that you know what a linear equation is, a linear algebraic equation. Here's an example of a linear equation in standard form. This is linear because the variables x and y are raised to the power of 1. A linear differential equation is a little different. A linear differential equation can be written in the following form. We have a sub n of x times the nth derivative of y with respect to x plus a sub n minus 1 of x times the n minus first derivative of y with respect to x. And we're going to continue this process. Notice the derivatives are descending in order down to the first derivative. And finally, the last term here, we have a naught of x as our coefficient function times the dependent variable y. So there's no derivative there. We can think of that as the 0th order derivative. This is equal to a function big F of x. So in this expression, each term has a coefficient function. We can refer to them all in general as a sub I of x. So that subscript I can be the real numbers or the natural numbers 0 up to n. These are functions of the independent variable. So notice I'm going to have a function of x here. It may not be a linear function. That could be x squared. That could be the square root of x. So classifying a differential equation as linear does not rule out the possibility of nonlinear coefficient functions. Specifically, a linear first-order differential equation can be written as dy over dx plus p of x times y equals q of x. So what we have up here is a general representation of an nth order linear differential equation. Nth order linear DE. It is linear in the dependent variable and its derivatives. So if I notice here, my dependent variable is y. Here is the first derivative of y with respect to independent variable x. And working our way back up, we have the n minus first derivative up to the nth derivative of y with respect to x. This differential equation is linear in the dependent variable y and its derivatives. But once again, that does not rule out nonlinear coefficient functions. Also observe that I've got the product of a function of x and another function of x right here. So it may not necessarily be true that a linear differential equation rules out products between variables. For example, if we think algebraically, the equation x times y equals 4, that is nonlinear because there's a product between x and y. So bottom line, how do we classify a linear differential equation? Y and its derivatives will not have any exponent. Remember, this notation here is not an exponent. This is an order of a derivative. If I see a derivative raised to an exponent, or if I see y raised to an exponent, that would be a nonlinear differential equation. So if we simplify this down to the first order case, this is the type of differential equation that we'll be examining in section 1.5. We have a first derivative, dy over dx, plus a function of x times y equals a function of x. When the differential equation is in this form, then we can solve it with the integrating factor method, and that's what we're going to learn next. This method is all about pattern recognition. It's really fascinating how it works out so nicely. An integrating factor for a differential equation is a function rho of x. That little letter there is the Greek letter rho, so we read it rho of x, such that the multiplication of each side of the equation by rho of x yields an equation in which each side is recognizable as a derivative. Once we introduce rho of x, we'll be able to solve it by direct integration, interestingly enough. So here's how. The first thing that's really important to this method is that we match our particular equation to this format. That is dy over dx plus a function of x times dependent variable y equals a function of x. When the equation is in this form, then our integrating factor will always follow the same predictable pattern. We're going to let rho of x, our integrating factor function, equal e to the integral of p of x dx. Okay, p of x comes from this coefficient right here. If the original equation is not in this order, then we will not get the integrating factor right. So again, it's very important that you match your differential equation to this form before you define your integrating factor. It's very similar to solving a quadratic equation with the quadratic formula. You know that when you apply the quadratic formula, your quadratic equation must be in that standard form before you identify a, b, and c. Once we have defined this integrating factor rho of x, we're going to multiply both sides by this integrating factor. So we've got three terms here in our differential equation, and we're going to multiply each of them by e to the integral of p of x dx. So we have e to the integral of p of x dx times the first term, dy over dx. I'm going to go ahead and distribute it. E to the integral of p of x dx times function p of x times y. And by the way, if you want to look at the dependent variable as a function of x, now is a convenient time to add that argument there. And then introducing our integrating factor on the right side, we have e to the integral of p of x dx times q of x. Now at this point, it may appear that we have complicated our differential equation, but I want you to look at patterns. Remember, this is all about pattern. The first thing that I want you to notice here is that I have a function y and its derivative is in this term. Okay, we've got the sum of two functions of x on the left side, and we're recognizing that if this is some sort of function, I'm just going to call it v, then its derivative lives over here. Okay, you may begin to recognize the possibility of the expansion of a product rule derivative over here on the left side. And that's exactly what you should recognize. To understand the pattern of the other terms, observe this to begin with. The derivative with respect to x, so I'm using differential operator notation here, big D sub x, that means the derivative with respect to x, of the integral of p of x dx. Okay, so notice I'm differentiating an integral. Those are two inverse functions, so they basically undo each other, and we end up with integrand p of x. This is important to recognize because if I notice here, I have a function e to the integral of p of x dx. I'm going to call that u. If I were to differentiate this function u, I would make a copy of the exponential exactly as it appears, and then I would multiply by the derivative of the exponent. Well, as we observed, the derivative of this exponent is right here. So if e to the rho of x, or e to the integral of p of x dx is u, then this term would be u prime. Now look carefully at the pattern of the left-hand side of this equation. We have a function u times derivative v prime plus the derivative of u, times v. So clearly we have the expansion of a product rule over here on the left side. When we recognize that pattern, then we can make the observation that the left-hand side is the derivative with respect to x of u, which is e to the integral of p of x dx, times v, y of x. And on the right side here, I'm just going to carry this information along as is. So here's why this method is so brilliant. By introducing this integrating factor, e to the integral of p of x dx, and multiplying each term by this integrating factor, then the left-hand side is the expansion of a product rule derivative. In fact, it's the derivative of the product of our integrating factor, e to the integral of p of x dx, times y of x. And remember, we're attempting to solve this differential equation for y of x. Once we observe that that left-hand side is the derivative with respect to x, and on the right-hand side we have a function of x, we can then integrate both sides with respect to x. So I'm going to integrate the derivative with respect to x. Listen to those inverse functions. I'm integrating a derivative, so that doesn't get us very far, right? But actually that's the key by which we're going to solve this differential equation. Right side's just a function of x, so we're going to integrate with respect to x. So looking at the big picture here, on the left side, we have the integral with respect to x of the derivative with respect to x. When you integrate a derivative, you end up with your original integrand. Therefore, executing the integral on the left side, we get the integrand, e to the integral of p of x dx times y of x equals the integral of e to the integral of p of x dx times q of x dx. Okay, and eventually when we execute that integral, we will obtain an arbitrary constant on the left side. What's our goal? Our goal is to solve this differential equation for dependent variable y, or function y of x. So one last step is necessary to solve this differential equation. We need to isolate y. So I'm going to multiply both sides by e to the negative integral p of x dx in order to cancel this term. So you can also think of that as dividing both sides by that integrating factor. Then we're going to multiply it by e to the integral of p of x dx times q of x dx plus c. And we have very cleverly solved this differential equation. Now, I don't consider myself to be clever. I have just learned this amazing method that someone else pioneered. The first person who was creative enough to develop this method that solves so many first-order differential equations. That's where the true genius lies, right? We're just following in their footsteps and learning their method. Now, at this point, don't be overwhelmed by the details. I know the notation is a little bit complicated there, but if you were able to follow the overall process, the overall pattern, you're going to see that in practice, you're actually going to be able to execute that integral up in the exponent of your integrating factor. And so when you apply that to both sides, it's not going to look so complicated. Let's go ahead and give this a try on example 1. Solve the differential equation 3xy prime plus y equals 12x using the integration factor technique. This is a first order linear differential equation. Notice it is linear in the dependent variable y and its first derivative. That is y and y prime, neither of those are raised to a power, so they are linear. Now, out of the context of section 1.5, if I needed to solve this differential equation, the first thing I would check would be, can I solve it by direct integration? So I would isolate y prime, and when I did that, I would obtain the function y prime equals 12x minus y over 3x. So clearly, we could not solve this by direct integration, because with our first derivative isolated, it's not equal to a function of x alone. So the first method that we learned, direct integration, is out. The second thing I would try would be to separate variables. But because in the numerator we have a difference of a function of x and y, not a product, we would be unable to solve it by separation of variables as well. So the two methods that we've learned so far do not apply, but we will be able to solve this one with the integrating factor technique. What's important to recognize about the integrating factor technique is that your original equation needs to be in the appropriate form. That appropriate form is the first derivative, dy over dx. Notice the coefficient of that first derivative is 1, plus some function of x times y equals some function of x. So we need to rearrange our equation to get it in this form. It's going to boil down to simply dividing all of those terms by 3x. When we do that, we're going to obtain y prime plus, I'm going to write it as 1 over 3x times y, and 12x divided by 3x equals 4. So here we can observe that the function p of x is 1 over 3x, and q of x happens to be a constant function 4. Since this first-order linear differential equation matches the form for the integrating factor technique, we can now define our integrating factor. So we will let rho of x equal e to the integral of p of x. Remember, p of x is 1 over 3x dx. So if we execute that integral up in the exponent, we have 1/3 times 1 over x. The antiderivative here is 1/3 times the natural log of the absolute value of x. Now, in the context of integrating in the exponent, you will not need the plus c, the arbitrary constant in that indefinite integral. We'll be able to pick that up later in the process. Now, applying properties of logarithms, let's move our coefficient to the exponent on the argument. We have natural log of the absolute value of x to the 1/3. And when we simplify, since we have base e raised to log base e, those two are inverse operations. They undo each other, and we end up with x to the 1/3. The argument falls down. Absolute value bars are negligible here. Again, we'll pick up an arbitrary constant to cover that later in the process. So the integrating factor that we need to apply to each term of our differential equation is x to the 1/3. So I'm going to go ahead and multiply every term by x to the 1/3. I'm going to distribute as I go here. So we have the original differential equation, or at least the one that we rearranged, where each term has been multiplied by this integrating factor. So let's go ahead and simplify this expression. I'm also going to rewrite that y prime as dy over dx. To me, it stands out a little better. It's easier to pick up on than y prime. Now, simplifying this term, I'm going to move the constant 1/3 to the left, and notice we have x to the 1/3 divided by x. We're dividing like basis, so we can subtract the exponents. Exponent 1/3 minus 1 would give me a new exponent, negative 2/3 times y. And I'm going to rewrite this 4 times x to the 1/3. Once we have introduced our integrating factor and simplified, our goal now is to recognize the left side as the derivative of some product. Okay, notice right here we have the function y, I'm going to call that one v, and its derivative lives right here, v prime. So we would expect this to be a function u, and we want to make sure that this is u prime. The derivative of x to the 1/3 is in fact 1/3 x to the negative 2/3. So that is u prime, which means we can recognize the left side as the derivative with respect to x of u times v. That is x to the 1/3 times y. We have a function of the independent variable alone left over there on the right side. So we are recognizing the left side as a function of x, therefore we can integrate with respect to x. And we will integrate both sides with respect to x. So it is reminiscent of direct integration. On the left side, we have two inverse operations paired. We have an integral with respect to x of a derivative with respect to x. Therefore, we end up with simply the integrand, x to the 1/3 times y. We will integrate directly on the right side using our power rule. So we're going to add 1 to the exponent and divide by that same value. When we add 1 to the exponent, we're going to end up with 4/3. And when we divide by 4/3, that's the same thing as multiplying by 3/4. So we'll go ahead and carry that operation out here. Now we're ready for that arbitrary constant of integration. We can simplify a little bit, and we're almost there. We have x to the 1/3 times y equals 3x to the 4/3 plus c. This is an implicit general solution. We need to make it explicit by solving for y. So you can divide all of the terms by x to the 1/3, or you can think of multiplying by x to the negative 1/3. So to show you where I'm going here, I'm going to multiply both sides by x to the negative 1/3. Both terms over here, including that constant. This isolates y on the left, and distributing here, we're going to add exponents. 4/3 minus 1/3 is 3/3, or 1, and we do have cx to the negative 1/3 here. So this is the general solution to the given differential equation. It is explicit, and it is general because of that arbitrary constant c. Now, did that really work? How can I tell if I really did obtain the correct solution? Well, remember, anytime you solve a differential equation, you can check by substitution. So let's take our given solution and find the first derivative. The first derivative of y, or y prime, would be 3 plus, or let's make it minus, c over 3 x to the negative 2/3. Whoops, how about negative 4/3, right? Need to subtract 1 from that exponent. We're going to plug this into the original differential equation, which was 3x y prime plus y equals 12x. So let's go ahead and substitute our y and our y prime in to see if we get a balanced equation. So I'm going to replace y prime with 3 minus c over 3 x to the negative 4/3, and I'm going to replace y with 3x plus cx to the negative 1/3. And we want to find out, does that give us 12x? So distributing here on the left side, we have 9x minus, distributing here and here, the 3's would cancel. We'd have c times x to the negative 4/3. So when I combine those exponents, 3/3 minus 4/3 gives me negative 1/3. Then we have 3x plus cx to the negative 1/3. Notice the cx to the negative 1/3 terms cancel. The left side is 12x, and that balances out with the right side. So we have, in fact, solved the differential equation correctly. So that is the method of an integrating factor. Remember, at this point now, you have 3 methods for solving differential equations. 1. Part 2, application mixture problems. Consider a tank containing a solution. Now, a solution is a mixture of solute, that's what's being dissolved, and solvent, that's what's doing the dissolving. For example, salt dissolved in water is an example of a solute in a solvent. Together, that makes the solution. So we have this volume in a tank of solution, right? Solute and solvent. We're going to assume both an inflow and an outflow. The inflow either increases or dilutes the solute in the solvent in the tank, and the outflow carries that volume out. So the amount of the solute, which we're going to call x of t, in the tank at time t is changing. We can write that as a function of t. T will represent time. We're going to model this with a first-order linear differential equation that can be solved with an integrating factor. So let's construct our model. What we are focused on is measuring the amount of solute in the tank at any time t. Again, we're calling that x of t. X of t is the amount of solute in the tank, And for example, we might measure the amount of solute in the tank in grams. Okay, I'm going to introduce some possible units here. Another thing to consider is the volume of the solution in the tank. So V of T, which may be changing with respect to time, again because we have an inflow and an outflow. This V of T is the volume of the solution in the tank. We might measure that in liters, for example. So the concentration of the solute in the tank at any time t will be the amount of solute in the tank per volume of solution. So the concentration at any time is X divided by V. Now, what affects the concentration in the tank is the inflow and the outflow. We need to consider a couple of things there. The first thing we need to consider is the rate of inflow. R sub I represents the rate of inflow. And possible units associated with the rate of inflow would be the liters, that measures volume, in time, possibly seconds. Another thing we have to consider is what's coming into the tank. Is it salt water? Is it pure water? Is it some proportion, some mixture that's coming in? C sub I represents the concentration in. Concentration coming in. We might measure this in grams of solute per liter of solution. These two aspects affect the outflow as well. R sub O, that's not R sub 0, but R sub O represents the rate of outflow. How fast is it draining? That will be measured in, for example, liters per second. And we also have to consider what's the concentration out. C sub O is concentration out. That might be measured again in grams per liter. So considering all these aspects and assimilating these in a model, we can say that the rate of change of solute in the tank at any time t is given by the rate of inflow times the concentration in minus the rate of outflow times the concentration out. To see how this model works, let's take a quick peek at the units. On the left side, we have X over T. X is measured in grams. T is measured in seconds, for example. So on the left side, our units would be grams per second. Now, looking at our two terms over here, the rate of inflow is liters per second. The concentration in is grams per liter. Same thing with rate out, concentration out. The rate of inflow is liters per second. Rate out is grams per liter. And if we cancel our common factors here, grams per second on the left matches the grams per second on the right. So looking at the units is always a good way to make sure that you have constructed your model appropriately. Now, this particular model was named by a former student that I had, Lily. She works in the Outreach Center. You might know her. She calls this the Ricci-Rocco model. That's a great way to memorize this. Ricci-Rocco. Rate in, concentration in, minus rate out, concentration out. Let's add just a little bit more detail to make this a very thorough model. The rate of change of X with respect to T, rate in, concentration in, Ricci, minus the rate out times the concentration out. Now remember, the concentration out is dependent on the changing amount of the solute in the solvent at any time. So the concentration out can be modeled by X of T divided by V of T. Observe that this is a linear first order differential equation. If we rearrange it into an appropriate form, we'll be able to solve this with the integrating factor technique. Let's try this model with example 2. A tank initially contains 60 gallons of pure water. So this is our initial amount in our volume. Brine containing 1 pound of salt per gallon enters the tank at 2 gallons per minute. And the perfectly mixed solution, we're oversimplifying it a little bit here, leaves the tank at 3 gallons per minute. Thus, the tank is empty after exactly 1 hour. So notice we have 2 gallons per minute coming in, 3 gallons per minute going out. So we're losing 1 gallon per minute. So after 60 minutes, the tank will be empty because we started out with 60 gallons. So I'm going to go ahead and draw a picture because it helps me to visualize the problem. I hope it helps you as well. We have our tank. We have inflow and outflow. So I'm assuming a cylindrical tank here. We have inflow and we have outflow, some sort of drain. From the information in the problem, we're told that the rate of inflow is 2 gallons per minute. So instead of liters on this problem, we're using gallons. And the concentration of brine is salt dissolved in water. So salt is the solvent, water is the solute, and brine is how we name that solution. The concentration coming in, we're told, is 1 pound per gallon. So we're measuring the salt in pounds this time instead of grams. We are also told that the initial volume, so at time 0, the volume in the tank is 60 gallons of pure water. So we are starting with pure water in the tank, and we have brine solution coming in and draining out. We're also told that the initial amount of salt in the tank is 0 pounds. The way that we know that is that we are told that the initial amount in the tank is pure water. So there's no salt in the tank to begin with. The rate of outflow, R sub 0, is 3 gallons per minute. And the concentration out, we're going to have to think about this one. The amount of salt flowing out of the tank is going to be given by the concentration in the tank at time t, x of t, divided by the gallons in the tank, right? So the pounds per gallon. Well, the volume of that tank is changing. We start with 60 gallons of water, and remember, because it's flowing in at 2 gallons per minute and out at 3 gallons per minute, every minute we're losing 1 gallon. So we're going to lose 1 gallon per minute, right? So if t is measured in minutes, after 1 minute, we'll have 59 gallons in the tank. After 2 minutes, we'll have 58 gallons in the tank, so on and so forth. So we could say that the volume is linear and it is decreasing. And looking at our units, this is pounds per gallon. So based on this information, we can set up our Ricci-Rocco model. Remember, we have the rate of change of x with respect to time is equal to the rate in times the concentration in minus rate out times the concentration out. Let's set up our model for this specific problem. So the rate of change of the amount of salt in the tank at time t, where time is measured in minutes, will be the rate in, that's 2 gallons per minute, times the concentration in, that's 1 pound per gallon, minus the rate out, 3 gallons per minute, times the concentration out. That's going to be x divided by 60 minus t. This is a linear first-order differential equation. We cannot solve it by direct integration or separation of variables. We will solve it with the integrating factor technique. Now, remember, we just learned that to use the integrating factor technique, our differential equation has to be in the specific form dy over dx plus p of x times y equals q of x. In that model, y is dependent, x is independent. Notice in our model, x is dependent and t is independent. So we're going to need to rewrite this in the form. Let's make a note here. We need the form dx over dt plus, not p of x, but p of the independent variable times the dependent variable equals a function of the independent variable. So we're just making a variable change here. So rearranging the given model, we're going to get dx over dt. I'm going to add this term to both sides, plus 3 divided by 60 minus t times x equals leftovers 2. Remember, the differential equation must be in that form in order to properly identify our integrating factor. So let's go ahead and do that. Our integrating factor, not rho of x this time, but rho of t, will be e to the integral of p of t. That's 3 over 60 minus t dt. If we integrate up there in the exponent, we're going to get e to the 3 times the natural log of the absolute value of 60 minus t. And because of the negative variable in the argument, we're going to get a negative for our integral. You can also pause and work that out with a quick U substitution to see that output. I'm sure that you can do that. So moving our coefficient to the exponent position and simplifying the combination of an exponential function with a logarithmic derivative, we can call our integrating factor 60 minus t to the negative 3. So we're going to apply that to all three terms of our differential equation. So we have 60 minus t to the negative 3 times dx over dt plus integrating factor 60 minus t to the negative 3 times 3 over 60 minus t x equals integrating factor 60 minus t to the negative 3 times 2. Let's simplify and see if we can recognize a derivative expanded according to the product rule on the left side. So simplifying, we have 60 minus t to the negative 3 times dx over dt, no change there. I'm going to rewrite this one as 3 times 60 minus t to the negative 4 x. Notice right here we have 60 minus t to the first power in the denominator. If we bring it out of the denominator into the numerator, that gives it a negative 1 exponent, and then we can add it to the negative 3 that we have here already. And on the right side, 2 times 60 minus t to the negative 3. Looking for the pattern of the product rule on the left side, we have a function here called x. I'm going to call that v. Its derivative lives right here. So if this is u, the derivative of this term, 60 minus t to the negative 3, if we apply the power rule, we'd end up with negative 3 times 60 minus t to the negative 4. I can see that right here, but remember, because of the chain rule, multiplying by the derivative of negative t, we'd get a negative 1. That would change that negative exponent we brought down in front to a positive. So this is, in fact, u prime. So we can rewrite that left side as the derivative with respect to t of function 60 minus t to the negative 3 times x. And the right side stays as is, 2 times 60 minus t to the negative 3. Since both sides are technically written as a function of t, we can now integrate both sides with respect to t. And I'm just going to add it in here. The left side's very easy. When we integrate a derivative with respect to t, we obtain the original argument, 60 minus t to the negative 3 times x. And we need to integrate over here on the right side. Now I want to be very clear of what I'm doing over here. So I'm going to evaluate this with the u substitution. U is 60 minus t. du would be negative dt. So I could rewrite this right side as 2 times the integral of u to the negative 3 times negative du. Okay, again, I can just move this negative over here so we can see we replace dt with negative du. For now, I'm just going to carry this left side down. Integrating here on the right side, we're going to add 1 to the exponent to get negative 2. We're going to divide by negative 2, but remember that negative 2 will cancel this negative, and then we're ready for a plus c. Looks like our 2's are going to cancel, and we can replace u with its original expression in x. So we obtain 60 minus t to the negative 3 times x equals u, that's 60 minus t to the negative 2 plus constant c. This is an implicit general solution. We need an explicit general solution. So we need to solve for x. I'm going to go ahead and multiply both sides by 60 minus t to the third power. That'll isolate x over there on the left side. So our explicit general solution then is x equals, let's distribute here, adding those exponents, we'd end up with 60 minus t to the first power plus c times 60 minus t to the third power. This is our general solution. Woohoo, we made it. So we constructed the model and then we solved it with an integrating factor. Now, can we go from general solution to particular solution? If I wanted to find that arbitrary constant c, I would need an initial condition involving x. And remember, we have it. We were told in the problem that there was pure water in the tank initially, which means at time 0, there were 0 pounds of salt in the tank. So I can plug 0 in for x, 0 in for t, and use that to solve for our arbitrary constant c. For this term, we have 60 cubed, that's 216,000. Solving for c, we'd end up with negative 60 divided by 216,000, which reduces to negative 1 over 3,600. So that's the value of our arbitrary constant. Thus, we can proceed from general solution now to particular solution. So I'm going to take my c value and plug it back in here. And our particular solution is x equals 60 minus t minus 1 over 3,600 times 60 minus t to the third power. That is our particular solution. So this will predict the amount of salt in the tank at any time t, where the salt is measured in pounds and the time is measured in minutes. So we began with the Ricci-Rocco model to set up our differential equation. We observed that it was first order linear that we could solve with an integrating factor. So we put the differential equation in the appropriate order and identified our integrating factor, applied that to both sides, integrated both sides with respect to t, and that gave us our general solution. Then from the problem, we got our initial conditions and applied them to our general solution now to get our particular solution. So we have a predictive model, that is, I can anticipate the amount of salt in the tank at any time t. Let's see if we can also answer the next question. What is the maximum amount of salt ever in the tank? Remember, we started with pure water, we have brine coming in, and we have also an outflow, so we want to know what's the maximum amount of salt that will ever end up in the tank. Since we have the function of t, x of t, our particular solution, that gives us the amount of salt in the tank at any time, I'm just going to rewrite it right here. We need to maximize this function. So think about it. How do you find the maximum of a function? Well, you're right back down to calculus 1. You need to find a derivative, set it equal to 0, get your critical values, and run either the first or second derivative test to determine if it's a max or a min. So let's do that. We'll find our first derivative, x prime of t, so we're differentiating with respect to t. The derivative of 60 is 0, and the derivative of negative t is negative 1. Applying the power rule over here in combination with the chain rule, we've got constant multiplier negative 1 over 3,600. We're going to bring the power down in front as a coefficient, keep the base the same, decrease the exponent by 1, and multiply by the derivative of the base. So just an ordinary derivative here. Simplifying, we have negative 1. If we combine the two negatives in that second term, that'll give us a positive. 3 over 3,600 reduces to 1 over 1,200 times 60 minus t squared. That's our first derivative. To find our critical points, we want to set our first derivative equal to 0 and solve for t. So I'm going to add 1 to both sides and then multiply both sides by 1,200. Then we can take the square root of both sides. If we think of 1,200 as 400 times 3, Square root of 400 is 20, and the square root of 3 we'll leave under the radical. So the square root of 1200 would give us plus or minus 20. Square root of 3, we do want the ability to give an exact answer so we can avoid rounding error. And solving for t, we're going to get t equals 60 minus or plus 20 square root of 3. That's the same thing as plus or minus. I'm just indicating that I moved that plus or minus 20 square root of 3 to the other side using the opposite operation. Once we have an exact answer, then we can approximate here at this step. I think an approximation will help us on the second derivative test. So using our calculator, 60 minus 20 square root of 3 gives us 25.36 minutes approximately. And then 60 plus 20 square root of 3 gives us 94.64 minutes approximately. So these are our critical values. At this point, we don't know if they yield a maximum or a minimum, so we will have to do further analysis to determine if we have found a maximum or the time at which the maximum occurs. Now, don't forget, in our original problem, we observed that the tank would be empty after 1 hour. 1 hour is 60 minutes. So even though this one is a critical point of the function, it does not apply to our particular situation. So we're only going to examine 25.36. Now, you can do either the first or the second derivative test to verify the maximum. I prefer the second derivative test, so I'm going to go ahead and find x double prime. I'm looking at my simplified first derivative here. The derivative of -1 is 0, and working on our second term there, we'd end up with 2 over 1200 times 60 minus t to the first power times -1. Or reducing and combining our negatives, we have -1 over 600 times 60 minus t. Let's make it even better. Let's distribute that -1 and call it t minus 60 over 600. So I'm going to take my critical point, which is approximately 25.36, and plug it into the second derivative. Notice our second derivative would then be negative. A negative second derivative indicates that we have a curve that is concave down, and if we are also at a critical point, that indicates that we have found a maximum. So remember, if your second derivative is negative, second derivative test indicates that you're dealing with a maximum. We could say, therefore, the maximum amount of salt is obtained at 25.36 minutes. However, we didn't quite answer the question, right? The question says, what is the maximum amount of salt? Well, to do that, we're going to take our time value and plug it back into the original function. So if I take x of, and you can do it exactly, 60 minus 20 square root of 3, go ahead and plug it in exactly and then approximate that with your calculator. You'd end up with approximately 23.09 pounds. Okay, so adding to our conclusion, the maximum amount of salt is approximately 23.09 pounds. So once you have that function, which models the amount of salt in the tank at any time, any minute, it's predictive and you can count on it. You can also analyze maximums, minimums, and all kinds of interesting things. Okay, I know what you're thinking. You're thinking, that was too easy. That's way too easy. I want something challenging. Okay, let's make it a cascade of tanks. Let's look at example 3. Consider the cascade of tanks shown below. So I've got tank 1 and tank 2. Both of them have inflow and outflow, and the amount in tank 1 is affecting the amount in tank 2. We're told that the volume, sub 1, V sub 1 is the volume in tank 1 is 100 gallons. I'm going to write it over here. V sub 1 is 100 gallons, and V sub 2 is 200 gallons. Those are our initial values. the volumes of brine in the two tanks. Each tank also initially contains 50 pounds of salt. That's an initial condition. We can observe that x of 0 here is 50 pounds, and if y of t is the amount of salt in tank 2, y of 0 is also 50 pounds. The three flow rates indicated in the figure are each 5 gallons per minute. So the rate of inflow from this first pipe is 5 gallons per minute, and the rate of outflow here is 5 gallons per minute. Okay, that means the rate of inflow into tank 2 is 5 gallons per minute, and the rate of outflow from tank 2 is 5 gallons per minute. Okay, this is good news. If the rate of inflow and outflow is the same for all three spots, that means that the volumes in the tanks remain constant. So V of t is 100, V sub 2 of t is 200. We won't have a changing volume function like we did on the previous problem. Notice it says pure water is flowing into tank 1. So the concentration of salt flowing into tank 1 will be 0 pounds per gallon. Let's look at the concentration. This is going to be flowing out of tank 1 into tank 2. This will be dependent on the amount of salt in the tank at time t, but again, because the volume is constant, it's going to be per 100 gallons. The concentration out of tank 2 is going to be the amount of salt in tank 2 at time t per 200 gallons. So again, this is pounds per gallon. This one also pounds per gallon. With all that information, we're going to do this one step at a time. First thing we want to do is model the amount of salt in tank 1 at time t. So the amount of solvent or salt in tank 1 is measured by x of t. So we'll apply the Ricci-Rocco model just to tank 1. So the rate of change of x with respect to time is going to be given by the rate in times the concentration in minus the rate out times the concentration out. So updating this with our specifics, the rate in is 5, concentration in is 0, that makes that term really easy, minus the rate out, also 5, times the concentration out. That is the amount of salt in the tank at time t per constant 100 gallons. Notice what we're dealing with when we simplify. We completely lose that first term, and we can reduce this to negative 1 over 20 times x. So observing that x is the dependent variable and t is the independent variable, we can solve this by separation of variables, right? We can't solve it by direct integration because I don't have a function of the independent variable on this side, but I can separate variables. We could rewrite this as 1 over x dx equals negative 1 over 20 dt. So we can solve this. We don't need the integrating factor method on this one. We can solve it very easily by separation of variables. So we integrate the left side with respect to x and the right side with respect to t. We'd obtain the natural log of the absolute value of x equals negative 1 over 20 times t, or negative t over 20 plus c. Solving for x, we'd end up with e to the negative t over 20 plus c. And as we've seen a couple of times now, we can rewrite that exponent on the right side as a product of like bases and simplify that e to a constant as a new constant. So ce to the negative t over 20 is the general solution for the amount of salt in tank 1 at time t. So this is our general solution for tank 1. Now we can go from general solution to particular solution if we apply an initial condition. So recall, we're told from the information given that the amount of salt in tank 1 at time 0 is 50 pounds. So using our general solution, I'm going to replace x with 50, and I'm going to plug in 0 for t. e to the 0th power is 1, so we can see that c is 50. So our particular solution then is x of t equals 50 times e to the negative t over 20. So look at the big picture. We have an exponentially decreasing amount of salt in tank 1, but the initial amount is that coefficient. We saw that in some of our previous models that we studied. So this is pretty exciting. We have half of our model in terms of a particular solution. The amount of salt in tank 1 at any time or at any minute is given by x of t, and x of t directly affects the amount of salt in tank 2, which we call y. So let's see how this is affected in the rest of our model. Part B, suppose that y of t is the amount of salt in tank 2 at time t. Show that dy over dt equals 5x over 100 minus 5y over 200 is the model, and then we'll solve for y of t. So looking back up here at our tank 2, we want to apply the Ricci-Rocco model to tank 2. So the rate of change of y with respect to time is rate in, concentration in, minus rate out, concentration out. The rate coming in into tank 2 is the rate coming out of tank 1. So the inflow for tank 2 is 5. The concentration coming in is the amount of salt from tank 1, which we call x of t, per constant 100 gallons of water. So there's my concentration in. The rate of outflow for tank 2, we are told, is 5 gallons per minute. We have that here. And the concentration going out is the amount of salt in tank 2 given by y per constant 200 gallons in the tank. So we have our Ricci-Rocco model applied to tank. Let's simplify our differential equation to dy over dt equals x over 20. And then we're going to cancel 5 into 200. That will give us 40. Observe from our Leibniz notation that our dependent variable is y and our independent variable is t. So on the right side, I see my dependent variable, but I have a little bit of a problem because I have a third variable introduced here. So we need to rewrite x as a function of the independent variable. And we can do that because we've already solved for x in terms of t. So I'm going to take 50e to the negative t over 20 and plug it in for x in this differential equation. That will give us dy over dt equals 50e to the negative t over 20 divided by 20 minus y over 40. So this is a linear first-order differential equation, and we can solve it with an integrating factor as long as we have it in the appropriate form. The form that we're going to need here, remember, we start with our derivative term. Then we have a function of the independent variable times our dependent variable, which in this case is y, equals a leftover function of the independent variable. Rearranging our specific differential equation in this form would give us dy over dt plus 1 over 40 times y equals, and let's reduce, 5 halves e to the negative t over 20. Once we have it in this form, we can appropriately identify our integrating factor. The integrating factor is always predictable. It's always defined from the same place. It's e to the integral of p of t, which in this case is 1 over 40 dt. That's an easy integral to evaluate. We would just end up with e to the t over 40. So that's our integrating factor, and we need to multiply each term in the differential equation by that integrating factor. So let's do that. We have e to the t over 40 times dy over dt plus e to the t over 40 times 1 over 40 y equals integrating factor e to the t over 40 times 5 halves e to the negative t over 20. Remember, at this point, our goal is to recognize a product rule expansion on the left side. So I'm going to start with this function y. I'm going to call that v and recognize that its derivative lives right here. So if we assume that this is the function u, we need to differentiate it. To differentiate e to the t over 40, we'd make a copy of the exponential and we would multiply by the derivative of the exponent, which is 1 over 40. So we can see we have u prime on this side. This means we can write the left side as the derivative with respect to t of u, that's e to the t over 40, times v, which is y. Simplifying over here on the right side, we'd have 5 halves and adding exponents, 1 over 40 minus 1 over 20. Think of that as 1 over 40 minus 2 over 40. We'll get negative t over 40. Now we are ready to integrate both sides with respect to t. Left side's easy. We simply get e to the t over 40 times y. On the right side, we have our constant multiplier e to the 5 halves. We make a copy of the exponential exactly as it appears, and then we divide by the derivative of the exponent. The derivative of the exponent is negative 1 over 40. Dividing by negative 1 over 40 is the same thing as multiplying by negative 40, and then we'll add our constant. I'm going to go ahead and simplify that right side and then worry about isolating y. Negative 40 times 5 over 2 would give us negative 100 times e to the negative t over 40, and we have our plus c. Okay, almost there. Let's isolate y by multiplying both sides by e to the negative t over 40, and that includes both terms over here on the right side. We would obtain y equals negative 100 times e. Now we're adding these exponents, right? So think negative 1 over 40 times t plus negative 1 over 40 times t. That's going to give me negative 2 over 40, or if we reduce, negative 1 over 20, which we can write negative t over 20, plus distributing here as well, right? C e to the negative t over 40. So we have arrived at the general solution, which models the amount of salt in tank 2 at any minute time t. To make it particular, we need to apply our initial conditions. Like for tank 1, we were told in the information presented in the problem that the initial amount of salt in tank 2, at the very beginning, was also 50 pounds. So I'm going to apply this to our general solution. That is, we're going to plug 50 in for y, and we're going to plug 0 in for t, and see if we can solve for c. We have 50 equals negative 100 times 1, e to the 0th power is 1, plus c times e to the 0th power, or c times 1. Looks like this constant is going to be 150. Therefore, we can say the amount of salt in tank 2 at any minute measured by t is negative 100 e to the negative t over 20 plus 150 e to the negative t over 40. So you learned a lot in this section. You learned how to solve a linear first-order differential equation using the integrating factor technique. You also learned how to do the Ricci-Rocco model applied to mixing a solvent in a tank. And you also observed a system of differential equations applied to a set of cascading tanks. So lots of good and useful skills in this section. Hope you learned a lot.